All right, guys, we're going to derive the one-dimensional wave equation. What you see here is just a part of a wave. It could be a string that's been attached to the left and the right of your screen. Um, Anyways, all we need to do is we need to analyze a small section of that. Now, what I've done here is I've taken the derivative of the wave equation at the point x. And I've done that to find what the tangent to the wave equation is, what angle it makes with the horizontal. And I've called that alpha. I've called that angle alpha. Likewise, I've found the tangent to the wave function at x plus dx. And I've called that angle beta. Okay? And so now when we're analyzing this string or whatever this is representing, whatever the wave is going through, we know that the material is not actually moving side to side. It's only vibrating up and down. So we only have to analyze the forces in the in the vertical direction. And so to do that, I'm going to look up here and see that T sine beta gives me the vertical component of the tension here. And if I subtract T sine alpha, that has to be equal to the mass of this part of the string times its acceleration. Now factoring out a t gives me sine beta minus sine alpha. Now my mass is going to be a linear density of the material. So it's going to be the mass per unit length. And then it's going to be multiplied by a length. Now, normally, you would get the linear density times the actual arc length. Okay? But in this particular case, we're going to look at where the amplitude of the wave is so small that it's very close to just being delta x. So in other words, when the amplitude is very small, our arc length is basically just delta x. So this is a very close approximation for small amplitudes. Okay, so this is our mass here. And then our acceleration is, of course, just partial square root of u over partial t squared. Now we need to make another approximation. I'm going to look at tangent theta. Now, theta is not a variable in any of this. We're just going to look at an equation here. I have tangent theta is equal to sine theta over cosine theta. And this is actually close to just sine theta when the absolute value of theta is much, much less than 1. So when theta is really small, cosine of basically 0 is just 1. And so we're just left with sine theta, really. So I can approximate sine theta here with just tangent of theta. Okay, so we're going to do that. I'm going to rewrite this as t times tangent of beta minus tangent of alpha, and that's equal to this. Now I know that tangent of beta is rise over run, which is my derivative. So this actually just gives me the derivative of u. Tangent beta is at this point here, is referencing this point here. And so it's at the value x plus delta x. Okay, so I have x plus delta x, and then I have my time component. Excuse me, that's a partial. And then I have, with respect to x, minus partial u at, we're referencing alpha, so it's just going to be at x over partial x. And then this is equal to my rho delta x partial squared u over partial t squared. Okay, so now I'm going to actually pull out the derivative operator to get partial over partial x Okay, so if I bring this operator back in, I get this. Okay, well, this here is just delta u. It's a small change in u. And so I can replace it with just delta u. Now, I'm going to actually rewrite this in a little bit different form. Let's write it as partial delta u over partial x. And this is equal to rho delta x partial squared u over partial t squared. Now if I divide both sides by delta x, this term here, or that delta x, comes down here. Now in the limit that delta x goes to 0, excuse me, in the limit that delta x and delta u go to 0, this becomes another partial derivative. So I'm left with t partial squared u up at the top over, and then partial x squared down at the bottom, and that is equal to rho partial squared u over partial t squared. And so now if I divide by rho, I get the typical form of the one-dimensional wave equation.